Hey guys, it's Math here. Oh wait, that's the other guy. Check him. That's the right guy. Well, it's Friday and I'm out again because my 2-year-old has an ear infection and has been removed from daycare. So I'm at home. But today I'd like to go over PV number 1 and PV number 2 and get you started on PV 3 and 4. I'm going to give you enough to get you going on those guys, and you should be successful in getting 3 and 4 done in class today and have no homework over the weekend. So really the lesson for today would have been, even if I was there, the same as this video, to go over PV1 and PV2, and then to check those two, and then kind of get you enough information to be fully successful on PV3 and 4. Okay, so without further ado, I'm going to go ahead and share my screen with you so that you can see my desktop. And we're going to kind of go over these together. Let me pull up my, hopefully you can see that now. And we're going to go over here and we're going to go ahead and publish these keys for you. So they will have been published by the time you walk in. You can check them. And the deal with the keys, I'm going to go ahead and talk through them. Keys aren't great tools to learn physics. They are good for checking your work. Sometimes you can see what you did wrong and figure it out. But in general, keys can be a bit difficult to kind of figure out or learn the physics. So let's go ahead and look at these though and talk about them. I'm going to go through each one, and if I need to go to my iPad, I will. So you can see for part A of this first one, you're just trying to figure out the temperatures T2 and T3 using that PV over T relationship, PV over T. And a lot of times you can isolate P or V depending on if you're going straight up with maybe an isovolumetric process or straight to the right with an isobaric process, a constant pressure process. You can isolate P or V. And so those are your two T's there. And that's just, again, from doing PV over T. One thing you can do here is get rid of the times 10 to the 3. If it's consistent throughout, you can kind of cheat a little bit, I suppose, as long as you're consistent with your units. Since PV over T equals PV over T, you can often get rid of those. But be careful with that, because if you're ever doing, say, PV equals nRT, you've got to include those powers, the times 10 to the 3 or times 10 to the negative 4. You've got to have those if you're calculating PV equals nRT. But sometimes if you're just doing PV over T and it's consistent throughout, you can negate this or neglect them. Letter B, 100 joules. And you might know that if I'm going, if the path is going clockwise, the overall work done is the area within the curve. But if I'm going clockwise, that overall area is going to be negative. Why? Because the higher piece, if I'm going clockwise, the higher piece is from left to right, and left to right is a positive volume change, therefore a negative work done. The gas is actually doing work, so the work done to the gas would be negative. If I'm going from right to left in a graph, right to left, then my volume change is negative. It's getting smaller. I'm compressing the gas, and therefore it's positive work. So if I'm going counterclockwise overall, counterclockwise through a full cycle, I'll end up with positive work. If I'm going clockwise through a full cycle, I'll end up with negative work if you follow those arrows. And that all comes from the top line moving either left or right. If I'm moving to the right on the graph, it's going to end up being negative work. If I'm moving to the left, it's going to be positive work. So my work total is always the area enclosed, half times base times height. That's an easy way to look at it. Now, what's interesting here is you can see sometimes College Board gives you alternative approaches. This alternative approach, rather than finding the area enclosed in the triangle, is actually to look at the individual areas of all 3 pieces. Well, for the straight bar up, that area is 0. But then as you go across the top of the triangle, that area would actually be the triangle and the rectangle below it, all negative. Then when you come back, that last motion from right to left would be the area in the rectangle, but that's positive. What happens is the negative area, that's the triangle and the rectangle, ends up negating some of that positive area by the rectangle. And so you're left with only the triangle, if that makes sense. The work done on the gas in one complete cycle is negative. So if you're a little confused up here with this positive 100, that's just saying what's the amount, how much work is done. Then down here in letter C, we're actually specifying that number should have been negative. If you put negative on the 100, you wouldn't be taken off. It wouldn't be points off. Letter D. Letter D is using that 3/2 nRT relationship I told you about. So going from 1 to 2, my temperature is certainly increasing, but with that being an isovolumetric process, the volume is not changing, the pressure is going up. I don't know what the internal energy is, so I can't really do a delta U as Q plus W unless I really know what's going on. You can see how that is what's happening here in terms of there's no work done. But to figure out that change in internal energy, that's going to be 3/2 nRT, where T is the difference in temperature, is the change from 300 up to 1500, or final 1500 minus initial 300. 3/2 N, the number of moles, R, 8.31 joules per mole Kelvin, and then the temperature change from 1 up to 2. I can find how much heat was added using 3/2 nRT. Cool. Okay, so that guy is published for you. Let's go together back to this guy and see about number 2 key. 2 key we did publish. Okay, so it's there. And you can see how PV 3 and 4 are ready to go for you. PV 3 and 4. Oh, those keys aren't there yet. They will be someday, but not yet. So let's go ahead and look at 2. So once again, in 2, you're working through temperatures, but this time you've got, let's see, I may have to go back to this question. Let's just check the answers and I can go back to the question and talk about it. T2 is 746, T3 is 560. Again, if you know the number of moles, you can use PV equals nRT and solve for T. PV from the graph equals nR, number of moles times 8.31, and you could actually just solve for T. Or if you know one of the temperatures, you can use your PV over T relationship, which is kind of what's happening here. Okay. All right. We can go back and talk about that if I need to. Let's do Checkinem first. So there's my work net, positive 6250. So that would be, again, work positive means I must be going counterclockwise in my rotation through the motion, counterclockwise. Letter C, for checking that heat is removed. What happens is for one full cycle, if I go all the way around from like the bottom left corner, all the way around back to the bottom left corner, if I end up at the same spot, I'm back to the same temperature. Temperature is proportional to the internal energy, delta U, or U. So if I'm back to the same temperature, my overall change in internal energy must have been 0. So then if you want to figure out for the cycle, if heat was gained or lost, I need to figure out for the cycle if work was done by or to the system. Is work positive or negative? If work is positive, because I was going counterclockwise, then I must have lost heat in the whole process, negative Q, the same number as the positive W, to end up back at the same internal energy, to have a delta U of 0. Does that make sense? So like if I go through a full cycle and I find out the work done is the area enclosed, and that work is positive 6,250 joules, then the heat lost must have been 6,250 joules. It must have been removed. If I was going clockwise, then my overall work done would be negative. But if I'm back at the same internal energy, then I must have gained heat in that process to end up back. Overall, I would have to gain heat, not in the individual one. I have to be careful with those. I can't guarantee that, but I can see by the way in which I'm moving, if work done is positive, then overall heat must have been lost. If work done is negative, then overall heat must have been gained. Okay, so you know what I'm going to do though, just to make sure I'm clear. You obviously just saw those answers. You can see them in your in the modules here at your leisure, your own time. I'm going to go through and just pull this guy up just to make sure I was very, very clear. So here we are going counterclockwise. You've got pressure, you've got volume, you've got a temperature. So because I know a temperature at state one, that means I certainly can find from the axes on the graph, the y and the x-axis, I can certainly find the temperatures at 3 and 2. So I don't actually need for those to do PV equals nRT. I can do my PV over T relationship. PV over T equals PV over T. Cool. I know that the net work done had to have been positive because from 2 to 3, I'm moving from right to left, 2 to 3. The higher bar is moving from right to left, meaning positive work done. That greater area is going to be positive. The net work is simply the area in the triangle. And so from 1 to 2, that area would be negative, and that's the rectangle basically from the line of 1 to 2 all the way down to the x-axis. But that would cancel out with the same area in the 2 to 3 process. So you're left with just the triangle. And because my work done ends up being positive, that means my overall heat must have been removed or lost to get back to square one. Okay, cool. So that's PV1 and PV2. Certainly going to move the test back to day 3 next week. There's not much on the agenda. The nuts and bolts of this chapter are these PV diagrams, being able to handle these questions. You've got PV 3 and 4 today. We've got a little bit more to do on day 1 next week. Excuse me, and then we'll review on day 2. So we should be in pretty good shape. This is a pretty short chapter. Before I let you go on 3 and 4, I'm going to go ahead and stop share here and go to my iPad, because I'd like to make sure that I give you all the materials you need or resources you need to be successful on PV 3 and 4. So let me get the old iPad going here, and then we will talk about those. Okay, iPad is coming, and I think you can see it now. Okay, so, little ramps. How much fun in physics can you have with ramps? Does that bring back stress, or is that relief? I don't know. Maybe PV graphs are not too bad when you start thinking about ramps and sliding forces. Okay, don't really know. For 3 and 4, it's a bit of the same, especially in number 3. Excuse me, but in number 4, I'm going to help you out. They give you a power output of an engine in watts. Excuse me. And they also give you an efficiency, which, again, if my efficiency is 20%, for instance, it's not in this problem, but if it were 20%, that ends up being 0.2. Excuse me. So if my power output's in watts, my efficiency is 20% or 0.2. This is, I think, a locomotive engine. It wants to talk about, for letter A, the heat in. So my output is so many watts. My efficiency is only 20% or 0.2. What heat was put in? Well, this gets confusing for students because they're saying, well, heat, that's Q. So for Q, I either need MC delta T. I don't have any of that stuff. I don't have mass. I don't have anything. I've got the power output in watts and I have an efficiency. So I don't have MC delta T. I don't have delta U and W work. So I can't do like delta U is Q plus W. So how do I get heat? This is just an efficiency problem. The heat input, and it actually says the rate at which heat is added in. That's the power in. The rate at which energy transfers is power. So all this letter A is an efficiency problem, because we know that efficiency is simply your out over your in. It says the rate at which heat is delivered to the engine. That's confusing for students. It's Q, right? Yes, but the rate at which heat is transferred in is actually a power. It's energy over time. That's the rate at which that happens. And that's the power input. You're given the output and the efficiency. It's not 0.2, but in decimal form, you can find the input. Then for letter B, I'll help you with this guy. It says, what are the magnitude of the resistive forces? Oh my goodness. If it's moving at a constant speed, yikes. Well, force. Where does force come into play with power? Power is work over time. Work is force times distance over time. It's weird because in this problem, they give you a velocity, power and velocity. Well, let's look at the units here. We typically think of force times distance over time, but what about force times distance over time? There it is. Turns out that a watt power is also force times velocity. We rarely see that equation. And in fact, I don't even think it's on your data sheet. So it's strange that this question is even there. It is on the APC data sheet, but it's been removed from the AP2 as far as I can see. So I don't really know why this question's in there, but it references, maybe it's just to finesse it, to figure it out, which I kind of like. Now, in terms of you're looking for force, but resistive force, they gave you a velocity check. You need resistive force. So which power do I use? Well, if you're moving at a constant speed, that means the resistive force equals the output force, or the resistive power equals the output power. So I don't know what the resistive power would be. That's a little bit funky, but it has to be equal to my output, not what I'm putting into the engine, because the input here includes heating up the engine, waste heat, blah, 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 blah. But moving at a constant speed means my resistive forces equal my output. So find that output power, put that here, divide by velocity, and you've got force. The rest of this problem, easy breezy mac and cheesy. It's the same stuff with the area and the curve and yada, yada, yada. Knock out 3 and 4, get it turned in, have a fantastic weekend. We'll go over 3 and 4 on day 1 next week on Monday. And then we'll kind of begin to wrap up the chapter because there's not much more. You've got your first law, delta U is Q plus W. Your second law actually is the efficiency, and that goes with entropy and disorder is really your second law. But I'm going to kind of bring it all together on day 1, and we'll have an open day review next day 2, test on day 3. Take care. God bless. Have a great weekend.